Okay. Okay. So next class will be the exam. Okay, on Thursday. So you'll get the whole day for complete your exam. Okay, and also you will get total 30 question for this time as well. So 45 minutes. Okay, keep in mind that one question you will get 1.5 minutes. Okay. But also I said the question all from this module 4. Okay, some of them will be MCQ and also true false, right? Okay. This time we'll get some more true false score question, okay, and then also MCQ question as well. Let's jump to our today's class. In our last class, we talked about the Peterson methods. It is one of the busy waiting solution. Let me share my screen. Okay, in our last class, we talked about the Peterson method, Peterson methods. Let me turn off my videos. Okay. Now let's see here. Okay. So far we learned the till Peterson method. What is this type of algorithm? This type of algorithm, as this is busy waiting solution. Okay, this is busy waiting solution. So for whatever we learn, it is busy waiting solution. What is the busy waiting solution? Busy waiting solution means that it's always executes whenever you schedule the process for entering the critical section. It always executes. Means that whenever you schedule a process for entering the critical sections, what's this? If a process inside this critical section, then what this process will do? Another process will execute in a unnecessary while loop. So always executes this kind of while loops. Okay, look through this kind of while loops. Okay, so this is called this busy waiting solutions. And so far we learned all of this busy waiting solution. Okay. Till Peterson is also busy waiting solution, but Peterson is the one of the best method for the busy waiting solution, because it's perform the it actually perform this all three. It granted all three properties for synchronization mechanisms. All three properties means that mutual exclusion is granted by these Peterson methods, as well as progress is granted by these Peterson methods. Also, bounded waiting is also satisfied the Peterson methods. Okay, so all three properties are granted by the Peterson methods. But problem is that these are the busy waiting solution. And let's take this. What is the problem for busy waiting solution? First one is it waste the CPU time. Okay, waste CPU time. All right. So it's waste the CPU time. Waste CPU time. Another problem is if it is priority based algorithm, scheduling algorithm. Priority based algorithm means that SJF and SRTF, LJF, this kind of algorithm is priority based algorithm. It is based on the shortest job first, based on the burst time or execution time. Okay, burst time or execution time. So these are the priority based algorithms. Okay, priority based, if your scheduler is priority based algorithm, so in that case, busy waiting solution actually provides a problems called the priority inversion problems. Okay, priority let me it's called as this priority inversion problems. Priority inversion. Okay, inversion problems. Okay, these are problems, priority inversion problems. If you use any priority based algorithms. What is the priority inversion problems? Let's check out what is the priority based inversion problems. Let's say you have total two process P1 and P2. Okay, P1, P2, you have total 2 processes, and let's check this. Process P1 is already inside this critical section. Process P1 is inside this critical section, and P1 is inside this critical section, and then executing the code from the critical section. Okay. Now let's check after when this process P1 enter the critical section. When process P1 enter this critical section, then if it is a log variables, or let's say in Peterson method, whatever it is, if a process inside this critical section, it will execute the while loop. Another process comes and it will execute the while loop. Okay, this kind of while loop until this process P1 completes its execution. Okay, then this is exit level code in here. Okay, now let's check. Let's check. This process P1 is inside this critical section, and P2 comes when process P1 is in this critical section, P2 comes inside this RAM, inside the RAM. Okay, P1 and P2. This process is now currently inside this RAM. Also P1, P2, it has this least execution time than the P1. Okay, if you consider this SJF method, so P2 is least execution time. So P2 will be scheduled by your operating system because P2 has the least burst time. Okay. Then now if you consider this assertive is preemptive algorithm, preemptive okay, preemptive algorithms. Okay, so it will stop this process P1 execution, and it will schedule the process P2. What process P2 will do? Process P2 will check this. Okay, one process is inside this critical section, so it always execute this while loop. Okay, it's always execute this while loop. Your operating system always priority process P2's priority is high and P1 is lower priority. So your operating system always schedule the process P2, and P2 will always execute the while loop because one process is inside this critical section already. P1 is inside this critical section, but your operating system cannot schedule the process P1 because process P1 it has this lower priority. Okay. Now let's see this carefully. This is no process actually cannot execute complete its execution in this situation. Okay? If it is priority based algorithm, this is actually known as this priority inversion problems. One process lower priority inside this critical section, and another process higher priority comes to the RAM, and your operating system always trying to schedule the process higher priority process P2, a higher priority process P2, and it will always execute this while loop because it cannot enter the critical section because already one process inside this critical section. Okay, that problems is called this priority inversion problems. Eventually, here is no process cannot complete its execution. Okay, but problem is that but this problem is happened when it is priority based algorithm. If you consider this FCFS, first come first serve, this is not priority based algorithm, so it doesn't have this types of problems doesn't occur for these FCFS algorithms. Also round robin is also another non-priority based algorithms. Okay, these problems is never happen for round robin as well. So this priority based inversion problems is happened only the SRTF some priority based algorithms. Okay, SRTF, LJF, okay, this kind of stuff algorithm. So this is the priority inversion problems. So these problems can happen if you use the busy waiting solution. So these are the problems for busy waiting solution. Now today let's see the what is the non-busy waiting solution. Okay. Now we'll check this. What is the non-busy waiting solution? Non-busy waiting solution is also known as the sleep wake up. Sleep wake up methods. Also block wake up method. Okay. Block wake up method. That is true. Now we talk about the non-busy waiting solution. Non-busy waiting solution. We talk about the non-busy solution. Non-busy solution is also known as the sleep wake-up methods as well as the block wake-up methods. It is implemented by using two system call, two function. One is called sleep function and another is wake function. Okay, wake-up function. Wake-up function. These two are the system function. System function means this function is inside this operating one of this, this operating system is one of the very large, thousands of millions of functions can be there. Okay, thousands of functions there. So it is one of the function. Sleep and wake up is one of the function of operating system. Okay. Now let's take this how you can implement this by how you implement or how you can implement the synchronization mechanism by using sleep and wake up methods. Okay, let me give you one example first, then it will be clear. Let's see, we have process. Let's take two process. It is fine. This is process one process one, or in simple, let's say P1, and another process is P2. Okay, two process. We have two process. Now we consider the BG or non-busy solution by using by using this non-busy mechanism, how you can implement the synchronization mechanism. Okay. Now let's check this. If process P2, it will check this. Process P1 check this. Process P2 inside critical section or not. Okay, it will check this process P1 inside this critical section or not. Then if it is, then it will call this sleep function. It will be in sleep mode, or the sleep mode is also known as the block state. Okay, block state, that's why it is block. Okay, sleep is also known as the sleep mode, or it will be turned into the block state. Okay, block state. It will check first, it will check this other process is inside this critical section or not. If it is, then it will be in sleep mode or block state. Next, either it will be inside this critical section. This is this two lines code for its entry section code for a critical section, and then another is exit section code. What is the exit section code? If this process P1 completes this critical section, it will wake up this another process. Another process is nothing but wake up process P2. From the sleep mode, it will be wake up, it will be in the ready state. Okay, block state to ready state. So this process will P1 will wake up the process P2. Okay, P2 process P1 will wake up this process P2 once it done its execution. Okay, completes execution. Now let's check this. What is the code for this process P2? Process P2 for entry level code, that it will be the if it will check this process P1 inside this critical section or not. Okay, process P1 inside CS. If process P1 inside this critical section, then what it will do? Process P2 will be the sleep mode. Sleep mode. This is the entry level code for process P2. Also, otherwise it will be enter this critical section. Let's check this another process. Another process is called this wake up. Entry level code is exit level code is wake up. It will call this wake up function, and it will, which process it will wake up? It will wake up this another process P1. P2 will wake up this process P1. P1 will wake up this process P2. Why? You see that process P1, what process P1 will do? If process P1 is interested in this critical section, it will check this process P2 inside this critical section or not. Okay. If it is not inside this critical section, then it will execute the critical section first. Okay, if process P1 is in P2 is in the sleep mode, it is sleep mode, then which process will wake up this process P2? Because process P2 actually went to sleep mode due to process P1 is inside this critical section, it is sleep mode. So process P1 responsibility for wake up this process P2. Okay, during this, after complete execution, then it will wake up this process P2. Similarly, for process P2, P2 will check this P1 inside this critical section. If it is let's say process P1 is currently inside this critical section, so P2 will be the sleep mode, and then sleep mode. Let's check in here. This is your RAM. Consider this is your RAM, and inside this RAM you have two process currently have the two process. Let me pen is off, but let me another pen. Okay, give me a minute, please. I'm changing my pen. Okay, so let's check in here. Okay, this is now pen is done. Okay, here is two process P1 and process P2. Now we are considering these two process. You know that this is the, let's say this is active or ready state process in here. Ready state process, this is the block state process in here. Okay, now let's take this process P1, you schedule the process P1, you schedule the process P1, schedule the process P1. What it will do, it will check this process P2 inside this critical section or not. Process P2 is not currently inside this critical section, then what it will do, it will be inside this critical section. Process P1 will be moves into the critical section, because it will check this if process P2 inside this critical section. If it is not, then it will be execute the enter the critical section. Now let's check this process P2 is scheduled by your operating system, and it will check this if process P1 inside this critical section. Currently process P1 inside this critical section, then what it will do, it will be sleep mode. Sleep means this block mode. Okay, block state, it will be moves to the in block state. Okay, whenever a process in block state, you know this operating system never schedule this process again until it's wake up or ready state. Okay, so it should be the wake up. Now let's check once this process, now only one process your operating system can schedule, because this process P1 is in ready state. Okay, process P1 is in ready state. Another process P2 is currently in block state or sleep mode. Your operating system never schedule the process from this block state. You know already. There is only one process in ready state. So operating system will schedule the process P1. Process P1 will complete its execution. Then it will check what it will do. It will wake up the process P2. Once it is wake up, then it will process P2 will be moves into the ready state. Wake up means that it will again moves to the ready state. Okay, process P1, P2 from this block state to ready state after calling this wake up system call. Okay, now you would again operating system, let's say P2 is scheduled by your operating system, and then P2 will check this P1 is inside this critical section or not. Here it will check this process P1 inside critical section or not. Now no process inside this critical section. Okay, P2 will be enter the critical section in here. Now let's check this process P1 again is scheduled by operating system. It will check this P2 inside this critical section or not. Here P2 is already inside this critical section. Then what it will do, P1 will be inside this sleep mode. So P1 will be the sleep mode or block state. So P1 will be in here, block state. It is now in block state. So here is only one process, then that can your operating system can schedule. So P2, once P2 completes its execution, then P1 will wake up this process P1. It will be back to block to ready state. Process P1 will be the ready state after calling this wake up function. Okay, so this is how a non-busy waiting mechanism works. Here you can see that instead of while loop, here you executes only a single if condition in non-busy waiting solution. But in busy waiting solution, we have every process we have this one while loop, non-busy. It keeps always busy. Okay. Another thing is that once the process is in sleep mode, it is in block state. So operating system, it has your operating system never actually schedule a process from this block state until it's wake up. Okay, so there is no way to waste the CPU time by scheduling the process that actually interested for entering the critical section. Okay, so here is a process. Let's say process P2, P1 is interested for entering critical section. It is now in sleep mode. Sleep mode means that this is block state. So your operating system will never schedule the process P1 until this process P2 wake up this process P1. Okay, process P1. P2 is wake up this process P1. Then again your operating system can schedule the process P2. So P1. So there is no way, and there is actually no way no way that for waste of CPU time like busy waiting solution, because in busy waiting solution all processing is in always ready state. So your operating system can always schedule a process from this ready state, and then it executes some unnecessary while loops. But in here, once a process inside this critical section, another process will be the sleep mode or block state, will be the block state. So here operating system never schedule the process from this block state until another process completes its execution from the critical section. Neither completes the execution from the critical section, and then it will wake up this another process. Now let's check this. Also, one thing you need to know this. Nowadays, all operating system follow the non-busy waiting solution, because it saves lots of CPU time. Okay, it saves lots of CPU time. This is the one of the main reason you use this non-busy waiting solution. Okay. Okay, this is kind of some overview of non-busy waiting solution. Here you sleep and also wake up problems by using sleep and wake up methods. And now let's check some other problems. How actually some formal problem for sleep and wake up methods. Okay. Now let's check one of the problems called the producer-consumer problems. So this is very famous problems in operating system. I mentioned this producer and consumer problem. Producer and consumer problem. Okay, producer and consumer problems. This is one of the famous problem in operating system. Producer and consumer, both are the process, different process. One process name is the producer process, and another process name is the consumer process. Consumer process. Actually, producer process generates some numbers. Okay, so before we here this producer and consumer process maintains a memory called the buffer. It's maintain a memory called buffer. In buffer there are some finite number of slot. Each slot can store a integer variable. That is buffer, and it has a finite number of slot. Is represented as variable called n. N value can be 100, can be 10, 20, 50, depending on the implementation. Okay. This is if it is 100, that is in buffer actually maintain this total 100 slot. Each slot can store a integer number. Okay, kind of like this. Let's check this slot here. Let's check. This is n value is 10. N value is 10. So here is total 10 slot. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So total 10 slot will be maintained by producer consumers methods or algorithms. We'll see these algorithms later, no worries. I just give you some overview how it works. When you when you run this producer process, then producer process will generate a number, and it insert to the slot a slot of, let's say, from this first slot, beginning slot, a slot of this buffer. Okay, and when you run a consumer process, it will remove a number from the buffer. Okay, producer process generates a number and it's inserted to the buffer. When you run this consumer process just remove a number from this buffer. Okay, this is how its producer consumer works. Okay, here is maintain a buffer, and once you run this producer process, it will generate, say, let's say, some number, random number, and it's inserted to the buffer. Whenever consumer process runs, it will remove a number from the buffers. Okay, now let's check how actually it's works. Okay, now let's check this. Another thing is that let me another variable is called this. Another variable is called this count variable. It manages one count variables. Count actually refers how many value is available currently, how many value is available inside this buffer. Okay, if your producer process run 3 or 4 times, let's say 3 times, so each time it will be executes a number, some random number, let's say 3 times 15, then your count value will be the 3. Therefore, there's currently 3 numbers inside this buffer. And another when true process is ready state, means this when consumer and producer is in ready state, then your operating system can schedule any of this process for a certain amount of times. And let's say if it is producer process, if it is producer process, if it is let's say it's scheduled for 5 units of time, and each units of time it can run one time it can run. So 5 units time it can insert the five number inside this buffer. If it is 10 numbers, let's say if it is 10 numbers, means that 10 units of time, or your operating system is the producer function or producer process a long amount of time. That times your producer process can fill up the buffer, all slot of this buffer. Okay, so producer process may fill out all slot of this buffer by inserting this number. Once this buffer is filled complete, then your producer process will be the sleep mode. Okay, will be the sleep mode, because there is no slot for inserting the number. Similarly, if your consumer process, what is actually consumer process will do? Consumer process will remove a number from this buffer. If it is scheduled for a long time, your consumer process will remove all of this number, and once it's remove this number, your count value will be also decreased. Okay, it will be decreased till 0. Once this count is 0, there is no number for deleting from this buffer. That time consumer process will be the sleep mode. Okay, then when you run a producer process, let's check this. Your consumer process is in sleep mode because it deletes all of this number from this buffer. Your consumer process is in sleep mode. This producer process actually runs again and enter a numbers. Let's say enter a number in a buffer. Then your consumer process actually it has on a number that can delete from this buffer. Already one number is inserted here, so your consumer process can delete a number. So in that case, your consumer process will be wake up. Similarly, when the producer process fill out this all of this buffer, 50, 90, 100, 101, and let's say 55. Okay, fill out all of this number. Once your consumer process will remove a number from this buffer. So here is one slot is empty, and your count value is now 10 is count value is 9. Once it is count value is 9, so here is at least one slot, then that actually where your producer can insert a number. So in that case, producer function will be the wake up. Wake up. So producer function will wake up by this consumer function, and consumer function will wake up the consumer function will wake up the producer function, and producer function will be wake up the consumer function. This is the basic idea for producer and consumer problems. Now let's write the code, then it will be more clear. Let me write this code. Means that here is CX kind of pseudo code. Okay, here is define n value. This means the number of slot this buffer. We consider this total 10 slot for a buffer. Also counter variables. Okay, once is counter variables is nothing but first it is 0, assigned to the 0, means that no there is no number inside the buffer. So now let's check this. What is the producer function? Thus producer function will do, it has two variables. It has two variables. Let's integer. It has two variables, num and integer nums. Num is local variables, one local variables. While this is infinite, one of the infinite loop, and then in this infinite loop, in num, it will generate a produce number. Produce num, and then it will check if count equal n, means that buffer is full, then it should be in sleep mode. This produce function should be inside the sleep mode. And next one is next thing is, otherwise it will insert number, whatever this num generates in here, it will insert this number to buffer. Also it will increase the count value, count equal count plus 1, and then it will again it will check if count equal 1, means that there is at least one value, then at least one value that can consumer can delete. So if it is count is 1, then this producer function will wake up this consumer function. Wake up consumer. Now this is the function for producer function. Let me write in here this consumer function as well. Void consumer. What it will do, it is also a number. It is a number, and then also this is a infinite while loop. Once your operating system schedule this function, it will run until actually it will run how long it's your operating system schedule this process or this process or function. Okay, count equal, if it is count equals 0, if count equals 0, then what it will do, this function will be sleep mode. That is nothing for consume or delete from this buffer. Otherwise it will remove the number from this buffer by using this function, remove num, remove this number, and then it will decrease this count value as well. Count equal count minus 1, and then it will check this another things. If count equal n minus 1, means that count is 9, means that there is at least one slot, then producer can insert a number. So it should be that time it should be wake up producer. If it is the condition is like this, if there is n minus 1, count value is n minus 1, once this produce, I'll explain it one by one. Let me finish it first. Okay, let's check this. What is the producer function will do? There is one local variable integer, and this is the infinite while loop. Once you schedule your producer process by your operating system, so if it is scheduled for a long time, it will schedule for a long time. Then what it will do? While loop will run again and again, and what it will do? It will produce a number. This is a produce function. Let's say this is the pseudo function, one of the function. This function will randomly creates a number, and it is insert this num variables. And if it is count equal num and count is 10, first 4, 5, 6, 7, 8, 9, 10. Okay. If it is count is n, count is at first count is 0, so n is 10, so it never be inside this never be in sleep mode. It is false. Then it will insert a number. Okay, insert a number, let's say 20 in here, and then count will be count equal 1. Count will be 1. Okay, and then if it is 1, let's say consumer function was in sleep mode, so it will be wake up this sleep function, or this function will be at the beginning. This function may be consumer function wake up, but it's called this again. It's called some unnecessary first time unnecessary call for wake up this consumer. It is fine. But if it is once it's run this while loop, it will always insert the number inside the buffer. Okay? 30, 40. Let's say it's scheduled for a long time and it's complete the buffer as well. 70, 80, 10, 21, 31. Okay, this numbers is already full up. Once it is again is trying to insert this number in here, what it will do? It will be producer will be sleep mode, because there is no slot for inserting the number. So producer function will be the sleep mode now. Producer in sleep mode. Producer in sleep mode in here. Okay, let's check. I track in here, and let's check again. Your consumer process is executed by your operating system. Once it will do, it will be count equal 0, but count here is currently 10. Okay, total 10 numbers. So count is now 10. So it will remove a number from in here. It will remove a number. Once it's here is also one while loop in while loop in here. Also consumer function is this is the while loop in here. Okay. Once this it is remove one, or once it's run one time, it will remove a number from the slot. So count value will be the decrement. It will be the 9. And then if count equal n minus 1, means that count equal 9, n minus 1 is 9. So it will wake up this producer function as well. Means that now there is only at least a slot where you can insert a number. Let's say again a producer function is scheduled by operating system. It insert a number. Here is 50, and it will be again, it will run, it will be inside this also the sleep mode as well. It means it's block state. Then only one function is consumer function will be scheduled by the operating system. And consumer function, let's say it's also scheduled by little bit a long time, and then by your operating system, then it will delete a number. Always it's delete a number. So it's a delete first, it will delete 50, that one also deleted in here. Delete, then count will be the 0. Count will be 0. Once this count will be the 0, then this consumer function will be the sleep mode. Will be the sleep mode of block state. Okay, block state, because there is no number for deleting. Okay. Now let's check this again. Your operating system schedule the producer function. Producer function. What it will do? It will produce a number. Okay, number, and then count equal n. No, count is now 0. Count is 0 here. It will not be sleep mode. So it will insert a number to the buffer. It will insert a number to the buffer, and then it will increase the count value. as a 1, it will be the 0 to 1. If it is 1, then it will wake up the consumer. So now consumer function here is 1, already count value is 1, so it will wake up the consumer function as well. Okay, let's say this is producer is currently wake up, consumer is in here. So this is ready state, this is block state, this is block state. So if it is 1, then it will be also the ready state. Consumer function is also the ready state. Both are in ready state now. Okay. Okay. This is how your producer consumer function is work. Now let's see that here is a problems. One problems for producer consumer problems. Let's figure out that what is the problems. Okay. Now let's see that. Let's see the consumer and producer problems again. How it looks. How it actually works. Now let's see that your operating system is schedule the process your producer process. Okay, producer process is scheduled by the operating system. Here is count equal 10. Okay, now let's check this operating system is schedule your producer function a little bit long time, and it will what's it will do, it will fill out the all of this slot by different number. Okay, okay, it is fill out this number, count is 10, count equal 10 now. Okay, once this count equal 10, then it will be the sleep mode. Let's say in this position it is in sleep mode. It is check this if condition, and then if count is okay, it is true. If count equal n, count equal 10, so count equal n equal 10, so it is in condition is true. It's execute this line, and before executing sleep mode, here it's after executing this if condition, your p function is printed by the operating system. Here actually it's execute this line, and then it's got the preemption by your operating system or CPU. So it's executes still if condition. Okay, if condition it was true, and then before executing is sleep, it actually it's got printed. Okay, now let's check this. Your consumer function is scheduled by your CPU. What it will do by your CPU for a little bit for a long time. So it will remove all of this number. Your consumer function remove all of this number again and again. Okay, by when it's execute this while loop, it's remove this all of this number and count become 0. Count becomes 0. Once this count becomes 0, your consumer function will be the sleep mode. Let's say your consumer function is now getting the sleep mode or block state. Okay, this is ready state. If you consider this is RAM, this is for this ready state process, this is for block state process. Okay, your consumer is now in block state. Okay, and then its count is 0 and it goes to the block state. Now your operating system is the process P1 again. So where the process P1 got preemption, where process P1 got process P got this preemption after the if condition. So it will execute after this if condition. Okay. So what is the after if condition? It will execute the sleep. So process P2 will be the sleep mode now. So P2 and both process P1, if it is producer as well as the consumer, both are currently in block state. Okay, block state. Now what's happened? Block state, and then both are block state. So both are block state in sleep mode. Both are in sleep mode. Okay. Now what's happened? Actually, process P1, there is no process. So operating system never schedule any process in here from here. So process now consumer process waiting for this process P1 will actually insert a number, and it will wake up this process. Consumer process. So consumer process is now waiting for this process P1 will insert a number, and it will wake up the consumer process. Also process P1 is now in block state. So process P1 is waiting for, okay, consumer process will delete a number, will remove a number, and then it will wake up the process producer process. Okay, so consumer process is waiting for this producer process. The producer process is waiting for this consumer process for waking up. But no process, actually both process is currently inside this block state. Okay, I think you got this point. So your code can your program can preempt at any from any instruction. Okay, after if condition, you see this after if condition, if producer process got preemption, then both process can be inside this block state. So process P1 P actually wait for this consumer process will wake up. Also consumer is also wait for C. Consumer is wait for the producer process for waking up. So no process actually currently is executing. So this is for circular waiting. This is also known as deadlock. Okay, deadlock problems. Both processes currently there is circular waiting. Both processes in sleep mode. So no process actually wake up to other process. So this is kind of circular waiting, also the deadlock. From here you can see this producer and consumer problems can be suffered by the deadlock problems. Now, if you look at carefully why these problems, this kind of situation is arise, in here if this process got preemption in this line for this entry level of code, this time preemption is so not entry level of code. In this logic, count equal 1, then it is sleep mode. Also here is also count equal this sleep mode. If it is preemption between this if condition, that time there will be problems like the deadlock. But if this logic you implemented in kernel mode or system mode, if you logic execute in kernel mode, that time there will be the when you before I said this kernel mode, or when actually you call a kernel function, or when you implement a logic inside this kernel mode, there will be the no preemption between to complete this logic or to complete this function. Let's say this is the function of this function. From this kernel function, you implement this process, this two line of code inside the operating system kernel. So once you call this function, kernel function, in kernel function never got preempted until it's complete. Okay, so if we implement this logic inside this operating system kernel, that time we can avoid this kind of situation or deadlock, because here we implement this count by using some ordinary user process. Okay, from ordinary variables inside this user process. But if we implement this two logic inside this operating system kernel, that time we can avoid this kind of situation. Okay, so how to do this? Implement this logic inside this kernel. So there is one way you can do this. It is called the semaphore variable. Okay, semaphore variable. Semaphores. Okay, semaphores variable. Now let's check this. What is the semaphore variable? The semaphore variable you can access only the kernel mode. While executing the operating system code, we can access this variable. Okay, it is this variable only access this kernel mode. If you maintain this count in a kernel mode, logic in a kernel mode, that time there will be the no preemption. Also, this kind of circular routing will not be occur. Okay, so this is the purpose of semaphore variables. Semaphore variables you can access only this kernel mode. We will see these details on it. Okay, so this can access only kernel mode. Okay, kernel mode. From user process you cannot access this semaphore type of semaphores variables. Okay, you need to access. You can access inside this kernel mode, and two types of semaphores. There are two types of semaphores available. two types of semaphore. We learn both of them. Two types of semaphores. First one is the binary semaphore. Binary semaphores, and second one is counting semaphores. Okay, two semaphores. Okay, two types of semaphores available. One is binary semaphores, another is the counting semaphore. Binary semaphore is also known as the mutex. This binary. Okay, first we'll learn the binary semaphore. Okay, of course, binary semaphore we'll learn first, then we'll learn the counting semaphore. Binary semaphore is also known as the mutex. Okay, mutex is nothing but mutual. It comes from the mutual exclusion. Mutex. Okay, mutex. Why it is called this mutex binary semaphore? Because it's always guarantee the mutual exclusion. That's why this binary semaphore is also known as the mutex. Also, another thing is that binary nowadays all operating system follow this binary semaphore, this binary semaphore to implement the synchronization mechanism. Okay, this is very popular, binary semaphores. Okay, binary semaphores, because it's always guarantee the mutual exclusion as well as the progress, as well as the bounded waiting. So we'll learn this. Now let's check this some other properties for semaphore variables. First of all, binary. Why it is binary semaphore? It takes only two value. Now, before I start this semaphore, let's see types. Actually, types of the semaphore. What kind of actually types contains a semaphore variables? If you consider the semaphore variables, semaphore is nothing but a structure type variables. Structure variable. You already know about this structure. C++ also C structure type variables. It contains two value. One is called val. It's a val. Another is called list. Another this is structure. Semaphore is structure type variables. It has two field. One is the val field. Another is list field. Okay. You can access this as .val or as dot, and that is if it is semaphore variable, and that is as dot list. Okay, two variables, two fields for this structure, semaphore structures. Val contains the, for binary semaphore, this val value contains only two values, 0 or 1, two values. Okay, what is the list called? List is nothing but similar as the array. Okay, it's kind of linked list. So what it will do? It will maintain a queue type list. Okay, queue type list. Okay, so value is nothing but either 0 and 1. This is that's why it is binary semaphore. Also, list will contain, or list will maintain a queue type list, first in first out. Okay, type list. It would be a linked list or anything maintained by linked list. So binary semaphore, it has two fields. It is structure type variables, and those contains two fields. One is value field, and another is list field. For binary semaphore, list field value field contain either value 0 or 1, and list maintain a queue type list. Okay. Now let's see that if in case of semaphore variable, if the value of value field contain if value is 1, if this value field is 1, means that means your the critical section, if this value, if this s dot val equal 1, if it is 1, that means the critical section is free. Critical section is free means that there is no process inside this critical section. If this value is zero, means that some process inside this critical section, inside the critical section. Okay. Okay, this is how actually bell field actually maintained. If it is 1, means that the critical section is free. A process can enter this critical section. If it is 0, that means that some process is not some process, actually one process inside this critical section. So it is not a free right now. So this so this process currently be in a sleep mode. Okay. Now let's check this how binary binary semaphores and its codes look like. It looks like this. It use two function. Let's check these two function. It use, this is the critical section. It contains binary semaphore use this kind of two function. It maintains by using these two function. One is the wait function. It passes the semaphore value. Also another, this is for entry level code for any process. If you have this, okay, this is it takes this parameter as a semaphore value parameters, wait function. It has a semaphore variables. And another is, and critical section, this is for entry level code. This is entry level code. Actually, it's called this function, entry level code. And what is the exit level code? Exit level code is the signal. Yes. Okay. This both wait and signal, these are the system function. System function or kernel. This both are this kernel or system function, okay? Wait and signal. By using this wait and signal, you can maintain the you can actually maintain the synchronization mechanism. Here, S is nothing but the semaphore. Value the parameter is semaphore parameters. Okay? Now let's check this how the wait and okay, the how wait and how okay. Before we enter the wait and signal function in details, let's check if you have this process, any number of process, P2, P4, P3, P4. If you have this number of process, total 4 process, and let's consider each process has critical section. All process has this critical section. This critical section. All process contains some critical section. So what you need to do? You need to do before and after this critical section. You need to call this wait function. You need to call this wait function in here, and also for exit section you need to call this signal function. Okay? Before critical section you need to call the same function. Okay, now this from here you can see that can this binary semaphore techniques, it is not a two process solution. You can use this binary semaphore technique for any number of process or any number of processes. So this is multi-process solution. You already know about this multi-process and two-process solution. Okay, multi-process solution. If you look at this lock variables and TSL lock mechanism as well as the TSL mechanism, it was multi-process solution. But for turn variable as well as another method, we learned this interested variables, mechanisms, and lastly we learn another process, Peterson. Both are two process solution. These all are these two process solution in for busy waiting solution. For busy waiting, lock and TSL was multi-process solution. Here semaphore is also binary semaphore is also the multi-process solution. It can be you open any number of processes, and each number of if each process contains some critical section, you can apply this binary semaphore techniques to maintain the uh, synchronization mechanism. Okay, so let's check. Okay, today we are almost running out of time. In our next class, we'll check this weight and signal function in detail. Okay, what is the weight and signal function and how the binary semaphore works. Okay, we'll check this in our next class. I already announced that in our next class we have our second midterm. Okay, in our second midterm Thursday, and you will get total 30 question as usual. Previous meet first, but you will get the 45 minutes. One question you will get 1.5 minutes. In this time you will get some more number of, I think, true false question than previous. Okay, so please take preparation from this module, from module 4. I think module 4. The questions are already 30 questions, so this is very small syllabus. Please carefully read every line of this of additional slide that I uploaded. Okay, in module 4. Every lines, please read carefully from this additional slide. Also, if you do not understand some from this slide, you of course you need to go through the lecture video as well. Okay, then it will be fine. It will be good for your preparation. The total 45 45 minutes. As usual, you can sit for this exam for the anytime Thursday 13th April. Okay, also once you open your exam, you'll get the 45 minutes. Okay, so do you have any questions or comment regarding today's class as well as your exam? Okay, if not, then we can stop here today and see you next class. Not next class, and next Thursday there will be the no class for next Thursday. So we'll meet again next week Tuesday. Okay, thank you and see you again.